Okay, so now we will talk about the hydrogen bond. Now, to understand hydrogen bond, we can talk again about the covalent bond and specifically the polar covalent bond. We talked already about the example of HCl. Okay, now let's see an example, another example actually for polar covalent bond would be the water, H2O. In water, we have an oxygen atom, right? And this oxygen atom has 6 electrons in its valence shell. And as we understand, it needs 2 more to get the octet rule, right? So there will be 2 hydrogen atoms. This is 1 and this is 2. Each one will contribute its electron into this polar covalent bond. So now, for now, the oxygen would have 8 electrons in its outermost shell, in its valence shell, whereas this hydrogen would have 2 and this hydrogen would have 2, as we saw before. The thing is, because of the attraction forces between the oxygen and the hydrogen, the differences are much more toward the hydrogen. This pair of electrons again will spend more time around the oxygen and this time around the hydrogen. The same thing for this pair of electrons. Will spend more time around the oxygen, this time around the hydrogen, exactly as we saw with the HCl. So this would make both hydrogen ions to display a slight positive, and the oxygen atom would display, or ion, it will display a slight negative charges. Now here it's displaying 2 slight negative charges because it received 2 extra electrons, right? So that's why it's displaying 2 minus negative. So this is the form. And again, the same thing as we talked about HCl. The netted charge of H2O is 0, is neutral, right? But when we zoom in and look at the individual atoms, we will find that the hydrogen are displaying slight positive charges, whereas the oxygen is displaying slight negative charges. Okay, this means that in a cup of water where we have hydrogen molecules, this is 1, this is 2, and this is 3, and of course here there will be another 1, here will be another 1, and so on. So here we will have the oxygen, hydrogen, and hydrogen. Here we will have oxygen, let's put 1 here, hydrogen, and then, or actually no, let's put this one the other way around. Oxygen, this is hydrogen, and this is hydrogen. Each one of these hydrogens is slight positive, the same thing here, slight positive. All of these hydrogens are slight positives, okay? And of course all of the oxygen are slight negative, 2 slight negatives. All of them are slight negative. So now, as you can see, there is a slight negative oxygen and slight positive hydrogen. So they will get attracted to each other. The same thing here. This hydrogen will get attracted to this oxygen. Okay? The same thing here. This hydrogen might get attracted to this oxygen. The same thing here. The same thing here. Oops, no. This should get attracted into the oxygen. This could get attracted into the oxygen. This will get attracted to this oxygen, and so on. So these attractions are the hydrogen bonds. Oh, sorry, not this one, not the last two. These between the hydrogen and the oxygen. So these are the hydrogen bonds. The attractions between the slight positive hydrogen ions and the slight negative oxygen ions of another water molecule, and it has to be of another, and it has to have hydrogen because it's a hydrogen bond. So any attraction between the slight positive hydrogen, and in this particular case it was oxygen, but it could be sulfate, it could be phosphor. Okay, so any attraction between the slight positive hydrogen and another slight negative atom will result in hydrogen bond. Now these are not like covalent bonds. There is no sharing of electrons, no exchange of electrons. It's just attraction. So no sharing or lose, or no gain, no lose. It's just attraction between the slight positive and slight negative. And therefore, these hydrogen bonds are super weak. These are extremely weak bonds that are constantly broken and reformed. As the second they break, the second they form, the second that they break, constantly. Even we don't see that in a cup of water. If you're looking at a cup of water, it will be like super stable. There is nothing there, but we know from this that constantly these water molecules are forming hydrogen bonds between them, and these hydrogen bonds are constantly breaking and reforming. Okay, so basically this is the hydrogen bond. Okay, let's move now to another topic, which is pretty straightforward. We'll start talking about chemical reactions. Now, bonds formation is a type of a chemical reaction. And for these chemical reactions, usually we will have components. We have the reactants. These are the materials getting into the chemical reaction. We have the products. These are the materials coming out of the chemical reaction. Usually we will have an arrow to indicate the way of the reaction, and we have numbers that indicate the number of, or the amount of, reactants and products. For example, here we have 2 A's and here we have 2 A's, and so on. So this is a very simple form of a chemical reaction. Now, based on the reactant and the products, we will have different types of chemical reactions. Basically 3 major types. The first one is synthesis. In this chemical reaction, we are starting with the small materials, okay, and we are forming long chain of products. So basically what we are doing is we are starting, basically what we are doing, we are starting with the small molecules and forming larger molecule. Okay, this is one type of chemical reaction. The other one is the decomposition. Decomposition chemical reaction, basically it's the opposite. We are starting with large molecule. We're starting with large molecule, and we are breaking it down to its original component. Okay, in this chemical reaction, the reactants are larger than the products. In the previous one, the reactants are smaller than the product. But here in this case, it's the other way around. And that's why it is a decomposition chemical reaction. That's why it's a decomposition chemical reaction. I lost my pen for a second, so sorry. Okay, the third type is an exchange chemical reaction. An exchange chemical reaction. Here what we will have, rearrangement of the reactants. For example, AB here, this was one reactant, C was a lone reactant, then we switched. AB plus CD will result in AD and CB. Here, or even here, there is no like small products and large products. or small reactants and large products. It could be rearrangement, just rearrangement of the atoms. Like say for example, in AOH plus HCl, that is in ACl, that's the water, that's the table salt and water. Now, some chemical reactions are reversed. This should appear as A plus B, okay, two arrows would result AB. It means that this reaction can go in either direction, from A plus B toward AB, or from AB toward A and B. And usually most of our body reactions are not reversible. Only very limited amount of chemical reactions in our body we can consider them reversible. Okay? Now, there are several factors that are affecting the rate of chemical reactions. You can read them. Okay? I'm not going to read from the slide just to save time. And this will take us to the chemistry of biological system. For this part, we are going to talk about the biochemistry, and it is the study of chemistry of biological system. And here, depending on the composition and chemical components of these compounds and molecules, we will have two types: inorganic compounds and organic compounds. The inorganic compounds are basically compounds or substances that they don't contain carbon and hydrogen, like water, salts, NaCl, acids and bases. These are all inorganic compounds. Whereas the organic compounds are substances that contain both carbon and hydrogen. Okay? And we will see like four major types: carbohydrates, fats, proteins, and nucleic acids. Let's start with water. 70% of our body is made out of water. Water, it has several characteristics. It acts as heat sink. It's a component of liquid mixtures, lubricant and cushioning, and it has a major role in chemical reactions. As a heat sink, it's because simply water can absorb heat. Like the same amount of water comparing to a steel, for example, the steel will turn red immediately, whereas water would remain water. Think of, for example, if you are making a cup of tea in a stainless steel pot. The stainless steel pot would immediately turn into red, and you can't touch it if it was empty. But if you put water in it, you can keep boiling you can keep it on fire for like 5 minutes. This is fire. I know you look, I know my drawings are really nice. Okay, so this is water. You can boil it for 5 minutes, or like keep it on fire for 5 minutes, and still you can put your hand in the water and nothing will, it's not burning. So this is because this is because water can absorb heat. It can absorb heat very slowly, and even it can release heat very slowly. Okay, I will put another video that shows an experiment, a very nice experiment that would prove this point. But in general, think of your cup of tea, okay, and the stainless steel pot. So this is what does it mean, water as a heat sink. Also, it's a component of liquid mixtures. These liquid mixtures, we will see like several types: solutions, colloids, and suspensions. All of them, the main component of them is water. Okay, could be like oil and water, or that they don't mix. Could be water and milk, could be water and juice, could be water with anything. Okay, but usually these liquid mixtures, the main component of them is water, and there are of three types: solutions, colloids, and suspensions. Solutions, we have here two materials or two substances. We have a solvent and solutes. Think of, for example, salt and water. The salt is the solute. Water is the solvent. You can dissolve salt completely in water, and it will disappear. You won't know that there is salt in it unless you taste it, right? That is a solution. So solutions are homogeneous, that the solute molecules are distributed evenly through the solution. So your first step or the last step, it doesn't matter, the same saltness of the water, and solutions do not precipitate or solutions do not precipitate or settle down over time. So for example, if you take a cup of water and you put salt in it and dissolve it, you can keep it for 3 days, and after 3 days you won't see any salt precipitated or settled down in the cup, right? And therefore, like water, that's because of water nature, is considered as universal solvent. We're talking, we said the example of salt, you can replace it with sugar, and the same would remain true. Now, because the nature of water is polar, as we saw with the regions of positive and negative electrical charges, that's why molecules could be liking water or disliking water. Polar molecules are usually hydrophilic, that they like water and they can dissolve easily in water, like HCl. HCl can dissolve easily in water. NaCl, the salt, can dissolve easily in water. But there are non-polar molecules that these are hydrophobic. They don't like water and they can dissolve in water, like oil, for example. Oil would always run away from water. It can't dissolve in water. Okay, that's these two substances. Polar molecules are hydrophilic, non-polar molecules are hydrophobic. Now, there are several ways to calculate the concentrations of solutes. There is the percentage, and see, for example, when they are saying 2% milk, it means 2 cups of fat and 98 cups of milk. Or when they are saying 10% juice, it means 10 cups of real juice in 90 cups of water, and so on. When we say like 1% salt, it's like 1 gram of salt in 99 gram of water, and so on. So this is the percentage. So there is one part of solute and 99 part of solution. 1 part of solute plus 99 part of solution, that is 100. And that is the 100 part of a solution in this sentence. So this is one way. Another way is milligram per deciliter. A deciliter is equals 1/10 of a liter. Okay, and this is usually more accurate comparing to this, more accurate measurement comparing to the percentage, and this is used usually in lab works. The third one is something called molarity. I'm not going to talk about it. It's even more accurate than the second way, and usually it's used for drugs. I'm not going to talk about it. We will not spend time. We will not see it in AB1 or AB2. Maybe later you will see it when you're in your nursing program or in your physician assistant program. Okay. The other type of solutions is the colloids. These are mixtures that somehow like heavy solutions. Think of, for example, milk, mayonnaise, whipped cream, all of these colloids, fog. Okay, all of these are colloids. Usually, they do not settle immediately, or they take long time to settle. Like for example, milk. If you leave a cup of milk in the fridge for like 3 hours or 4 hours, that's fine. 3 to 4 hours, or maybe even 1 day, or several days even, that's fine. But if we leave it, for example, for 14 days, or like 1 month, you will see at the end that there are fat down and the water remained on the top. That's exactly what does it mean colloid. Okay, same thing for mayonnaise. If you leave mayonnaise like for like 14 days or more, or actually even more than 14 days, eventually you will see it's precipitated and there is water on the surface. Same thing for yogurt. You know, yogurt, once you open the yogurt package, right, and you will leave it like for a couple of days, you will see water floating on the surface. This is the bulk of the yogurt, and there is water on the surface because yogurt settled. Yogurt is a colloid. Okay, you can remix it and eat it. That's nothing wrong with it. Nothing wrong with that water. It's not ruined. It's just because it's settled. And the third type is suspensions. Now here with suspensions, usually these are heavy solutes. So like for example, water and sand. You can put sands in water and stir it, right? And you will see the sand all over the place. Once you stop, the sand will go to the bottom directly, right? So this is suspension. Blood, for example, is a suspension. If you take like a cup of blood and leave it for 1 day, you will see it's precipitated. There are things settled down. So blood is a suspension. Also, water works as lubricant and cushion. It's a major component of many of body's lubricant fluids, like synovial fluid. We'll see this in joints. Cushioning, we will see it in the brain. That it's protecting cells and organs from physical trauma. As again, we will see that in the brain. We will see it in AB2 in the eyes. Okay, all of these are functions of water. Now, water involvement in chemical reactions comes in two forms, either in dehydration synthesis or hydrolysis. Dehydration synthesis, remember synthesis, we said two small particles, in this case monomers, okay, forming one larger particle. That's synthesis. Now, dehydration synthesis, because we are taking hydrogen molecule, we are taking water molecule out of the two monomers. So as you can see, in order to join these, we have to take water molecule out. That's why it's dehydration. D, it means remove. Hydration, water. So this is like removing water synthesis reaction. That's the dehydration synthesis. The opposite would be hydrolysis. Hydrolysis involves the re-addition or the addition of the water molecule. So we have this big structure, okay? We want to break this bond, simply add water. Each monomer would break and restore its original format. This is the hydrolysis. So these two reactions, the dehydration synthesis and hydrolysis, are like 98% of reactions in our body. Most of the reactions in our body are falling between either one, either hydrolysis or dehydration synthesis. Dehydration synthesis for building, okay, like building a protein, for example. Here for breaking down. You see all the food you are eating, it needs to be broken down to the basic substances. This is happening through hydrolysis reactions. Another thing for the salts, that's part of how water help in chemical reactions, that salts are easily dissociated in water. They're completely going to dissolve. If you drop like a few drops of salts or few blocks of salts in water, whether you stir them or not, just wait like for 5 minutes and the salt will be gone. Basically because the water molecule by its nature, we said this is like a polar molecule, it will get attracted. And remember the salt is a covalent bond, and we said, it's ionic bond. And we said with the ionic bond, the salt, the sodium and the chloride, the sodium would lose completely its electron and the chloride will keep that electron. So when we put them in water, they will break because the chloride is already negative, okay? It has another extra electron. So these hydrogen molecules would try to get attracted, they'll try to establish a bond with the chloride. Okay? And on the other side, the oxygen will try to establish a bond with the positive sodium. It will get attracted to it. That's why salts are easy to dissolve in water. Okay? And usually salts are a product of ionic bonds. Okay? The salts are products of ionic bond. Okay, so I will stop here. I want you to take a break, write your questions, think about what we saw so far, and then when we come back, we will talk about the acids and bases.